Humans have always looked at the heavens and wondered about the nature of the objects seen in the night sky. With the development of rockets and the advances in electronics and other technologies in the 20th century, it became possible to send machines and animals and then people above Earth's atmosphere into outer space. Well before technology made these achievements possible, however, space exploration had already captured the minds of many people, not only aircraft pilots and scientists but also writers and artists. The strong hold that space travel has always had on the imagination may well explain why professional astronauts and laypeople alike consent at their great peril, in the words of Tom Wolfe in The Right Stuff, 1979, to sit on top of an enormous Roman candle, such as a Redstone, Atlas, Titan or Saturn rocket, and wait for someone to light the fuse. It perhaps also explains why space exploration has been a common and enduring theme in literature and art. As centuries of speculative fiction in books and more recently in films make clear, one small step for man, one giant leap for mankind was taken by the human spirit many times and in many ways before Neil Armstrong stamped humankind's first footprint on the moon. Achieving spaceflight enabled humans to begin to explore the solar system and the rest of the universe, to understand the many objects and phenomena that are better observed from a space perspective, and to use for human benefit the resources and attributes of the space environment. All of these activities, discovery, scientific understanding, and the application of that understanding to serve human purposes, are elements of space exploration. For a general discussion of spacecraft, launch considerations, flight trajectories, and navigation, docking, and recovery procedures, see spaceflight. Motivations for space activity. Although the possibility of exploring space has long excited people in many walks of life, for most of the latter 20th century and into the early 21st century, only national governments could afford the very high costs of launching people and machines into space. This reality meant that space exploration had to serve very broad interests, and it indeed has done so in a variety of ways. Government space programs have increased knowledge, served as indicators of national prestige and power, enhanced national security and military strength, and provided significant benefits to the general public. In areas where the private sector could profit from activities in space, most notably the use of satellites as telecommunication relays, commercial space activity has flourished without government funding. In the early 21st century, entrepreneurs believed that there were several other areas of commercial potential in space, most notably privately funded space travel. In the years after World War II, governments assumed a leading role in the support of research that increased fundamental knowledge about nature, a role that earlier had been played by universities, private foundations, and other non-governmental supporters. This change came for two reasons. First, the need for complex equipment to carry out many scientific experiments and for the large teams of researchers to use that equipment led to costs that only governments could afford. Second, governments were willing to take on this responsibility because of the belief that fundamental research would produce new knowledge essential to the health, the security, and the quality of life of their citizens. Thus, when scientists sought government support for early space experiments, it was forthcoming. Since the start of space efforts in the United States, the Soviet Union, and Europe, national governments have given high priority to the support of science done in and from space. From modest beginnings, space science has expanded under government support to include multi-billion-dollar exploratory missions in the solar system. Examples of such efforts include the development of the Curiosity Mars rover, the Cassini-Huygens mission to Saturn and its moons, and the development of major space-based astronomical observatories, such as the Hubble Space Telescope. Soviet leader Nikita Khrushchev in 1957 used the fact that his country had been first to launch a satellite as evidence of the technological power of the Soviet Union, and of the superiority of communism. He repeated these claims after Yuri Gagarin's orbital flight in 1961. Although US President Dwight D. Eisenhower had decided not to compete for prestige with the Soviet Union in a space race, his successor, John F. Kennedy, had a different view. On April 20, 1961, in the aftermath of the Gagarin flight, he asked his advisors to identify a space program which promises dramatic results in which we could win. The response came in a May 8, 1961, memorandum recommending that the United States commit to sending people to the moon, because dramatic achievements in space symbolize the technological power and organizing capacity of a nation, and because the ensuing prestige would be part of the battle along the fluid front of the Cold War. From 1961 until the collapse of the Soviet Union in 1991, competition between the United States and the Soviet Union was a major influence on the pace and content of their space programs. Other countries also viewed having a successful space program as an important indicator of national strength. Even before the first satellite was launched, US leaders recognized that the ability to observe military activities around the world from space would be an asset to national security. Following on the success of its photo reconnaissance satellites, which began operation in 1960, the United States built increasingly complex observation and electronic intercept intelligence satellites. The Soviet Union also quickly developed an array of intelligence satellites, and later a few other countries instituted their own satellite observation programs. Intelligence-gathering satellites have been used to verify arms control agreements, provide warnings of military threats, and identify targets during military operations, among other uses. In addition to providing security benefits, satellites offered military forces the potential for improved communications, weather observation, navigation, timing, and position location. This led to significant government funding for military space programs in the United States and the Soviet Union. Although the advantages and disadvantages of stationing force delivery weapons in space have been debated, as of the early 21st century, such weapons had not been deployed, nor had space-based anti-satellite systems, that is, systems that can attack or interfere with orbiting satellites. The stationing of weapons of mass destruction in orbit, or on celestial bodies, is prohibited by international law. Governments realized early on that the ability to observe Earth from space could provide significant benefits to the general public apart from security and military uses. The first application to be pursued was the development of satellites for assisting in weather forecasting. A second application involved remote observation of land and sea surfaces to gather imagery and other data of value in crop forecasting, resource management, environmental monitoring, and other applications. The US, the Soviet Union, Europe, and China also developed their own satellite-based global positioning systems, originally for military purposes, that could pinpoint a user's exact location, help in navigating from one point to another, and provide very precise time signals. These satellites quickly found numerous civilian uses in such areas as personal navigation, surveying and cartography, geology, air traffic control, and the operation of information transfer networks. They illustrate a reality that has remained constant for a half-century. As space capabilities are developed, they often can be used for both military and civilian purposes. Another space application that began under government sponsorship, but quickly moved into the private sector, is the relay of voice, video, and data via orbiting satellites. Satellite telecommunications has developed into a multi-billion-dollar business and is the one clearly successful area of commercial space activity. A related, but economically much smaller, commercial space business is the provision of launches for private and government satellites. In 2004, a privately financed venture center piloted spacecraft, Spaceship One, to the lower edge of space for 3 brief, suborbital flights. Although it was technically a much less challenging achievement than carrying humans into orbit, its success was seen as an important step toward opening up space to commercial travel, and eventually to tourism. More than 15 years after Spaceship One reached space, several firms were poised to carry out such suborbital flights. Companies have arisen that also use satellite imagery to provide data for business about economic trends. Suggestions have been made that in the future other areas of space activity, including using resources found on the Moon and near-Earth asteroids and the capture of solar energy to provide electric power on Earth, could become successful businesses. Most space activities have been pursued because they serve some utilitarian purpose, whether increasing knowledge, adding to national power, or making a profit. Nevertheless, there remains a powerful underlying sense that it is important for humans to explore space for its own sake, to see what is there. Although the only voyages that humans have made away from the near vicinity of Earth, the Apollo flights to the Moon, were motivated by Cold War competition, there have been recurrent calls for humans to return to the Moon, travel to Mars, and visit other locations in the solar system and beyond. Until humans resume such journeys of exploration, robotic spacecraft will continue to serve in their stead to explore the solar system and probe the mysteries of the universe. Major milestones: the first artificial Earth satellite, Sputnik 1, was launched by the Soviet Union on October 4, 1957. The first human to go into space, Yuri Gagarin, was launched, again by the Soviet Union, for a one-orbit journey around Earth on April 12, 1961. Within 10 years of that first human flight, American astronauts walked on the surface of the Moon. Apollo 11 crew members Neil Armstrong and Edwin Buzz Aldrin made the first lunar landing on July 20, 1969. A total of 12 Americans on 6 separate Apollo missions set foot on the Moon between July 1969 and December 1972. Since then, no humans have left Earth orbit, but more than 500 men and women have spent as many as 438 consecutive days in space. Starting in the early 1970s, a series of Soviet, Russian from December 1991, space stations, the US Skylab station, and numerous space shuttle flights provided Earth orbiting bases for varying periods of human occupancy and activity. From November 2, 2000, when its first crew took up residence, to its completion in 2011, the International Space Station, ISS, served as a base for humans living and working in space on a permanent basis. It will continue to be used in this way until at least 2024. Since 1957, Earth-orbiting satellites and robotic spacecraft journeying away from Earth have gathered valuable data about the Sun, Earth, other bodies in the solar system, and the universe beyond. Robotic spacecraft have landed on the Moon, Venus, Mars, Titan, a comet, and 3 asteroids, have visited all the major planets, and have flown by Kuiper Belt objects and by the nuclei of comets, including Halley's Comet, traveling in the inner solar system. Scientists have used space-derived data to deepen human understanding of the origin and evolution of galaxies, stars, planets, and other cosmological phenomena. Orbiting satellites also have provided, and continue to provide, important services to the everyday life of many people on Earth. Meteorologic satellites deliver information on short and long-term weather patterns and their underlying causes. Other Earth observation satellites remotely sense land and ocean areas, gathering data that improve management of Earth's resources and that help in understanding global climate change. Telecommunications satellites allow essentially instantaneous transfer of voice, images, and data on a global basis. Satellites operated by the United States, Russia, China, Japan, India, and Europe give precision navigation, positioning, and timing information that has become essential to many terrestrial users. Earth observation satellites have also become extremely useful to the military authorities of several countries as complements to their land, sea, and air forces and have provided important security-related information to national leaders. As the many benefits of space activity have become evident, other countries have joined the Soviet Union and the United States in developing their own space programs. They include a number of Western European countries operating both individually and, after 1975, cooperatively through the European Space Agency, as well as China, Japan, Canada, India, Israel, Iran, North Korea, South Korea, and Brazil. By the second decade of the 21st century, more than 50 countries had space agencies or other government bodies carrying out space activities. History of space exploration. Since ancient times, people around the world have studied the heavens and used their observations and explanations of astronomical phenomena for both religious and practical purposes. Some dreamed of leaving Earth to explore other worlds. For example, the French satirist Cyrano de Bergerac in the 17th century wrote Histoire comique des États et Empires de la Lune, 1656, and Histoire comique des États et Empires du Soleil, 1662, together in English as A Voyage to the Moon, with some account of the solar world, 1754, describing fictional journeys to the Moon and the Sun. 2 centuries later, the French author Jules Verne and the English novelist and historian H. E. Wells infused their stories with descriptions of outer space and of spaceflight that were consistent with the best understanding of the time. Verne's De la Terre à la Lune, 1865, From the Earth to the Moon, and Wells's The War of the Worlds, 1898, and The First Men in the Moon, 1901, used sound scientific principles to describe space travel and encounters with alien beings. In order to translate these fictional images of space travel into reality, it was necessary to devise some practical means of countering the influence of Earth's gravity. By the beginning of the 20th century, the centuries-old technology of rockets had advanced to the point at which it was reasonable to consider their use to accelerate objects to a velocity sufficient to enter orbit around Earth and even to escape Earth's gravity and travel away from the planet. Tsiolkovsky, the first person to study in detail the use of rockets for spaceflight, was the Russian schoolteacher and mathematician Konstantin Tsiolkovsky. In 1903, his article Exploration of Cosmic Space by Means of Reaction Devices laid out many of the principles of spaceflight. Up to his death in 1935, Tsiolkovsky continued to publish sophisticated studies on the theoretical aspects of spaceflight. He never complemented his writings with practical experiments in rocketry, but his work greatly influenced later space and rocket research in the Soviet Union and Europe. Goddard. In the United States, Robert Hutchings Goddard became interested in space exploration after reading works such as The War of the Worlds. Even as a young man, he dedicated himself to working on spaceflight. In his 1904 high school graduation speech, he stated that it is difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow. Goddard received his first 2 patents for rocket technology in 1914, and, with funding from the Smithsonian Institution, he published a theoretical treatise, A Method of Reaching Extreme Altitudes, in 1919. Goddard's claim that rockets could be used to send objects as far as the moon was widely ridiculed in the public press, including the New York Times, which published a retraction on July 17, 1969, the day after the launch of the first crewed mission to the moon. Thereafter, the already shy Goddard conducted much of his work in secret, preferring to patent rather than publish his results. This approach limited his influence on the development of American rocketry, although early rocket developers in Germany took notice of his work. In the 1920s, as a professor of physics at Clark University in Worcester, Massachusetts, Goddard began to experiment with liquid-fueled rockets. His first rocket, launched in Auburn, Massachusetts, on March 16, 1926, rose 12.5 meters, 41 feet, and traveled 56 meters, 184 feet, from its launching place. The noisy character of his experiments made it difficult for Goddard to continue work in Massachusetts. With support from aviator Charles A. Lindbergh and financial assistance from the philanthropic Daniel Guggenheim Fund for the Promotion of Aeronautics, he moved to Roswell, New Mexico, where from 1930 to 1941 he built engines and launched rockets of increasing complexity. Obert, the third widely recognized pioneer of rocketry, Hermann Obert, was by birth a Romanian but by nationality a German. Reading Verne's From the Earth to the Moon as a youth inspired him to study the requirements for interplanetary travel. Obert's 1922 doctoral dissertation on rocket-powered flight was rejected by the University of Heidelberg for being too speculative, but it became the basis for his classic 1923 book Die Rakete zu den Planetenräumen, The Rocket into Interplanetary Space. The work explained the mathematical theory of rocketry, applied the theory to rocket design, and discussed the possibility of constructing space stations and of traveling to other planets. In 1929 Obert published a second influential book, Wege zur Raumschifffahrt, Ways to Spaceflight. His works led to the creation of a number of rocket clubs in Germany as enthusiasts tried to turn Obert's ideas into practical devices. The most important of these groups historically was the Verein für Raumschifffahrt, VFR, Society for Spaceship Travel, which had as a member the young Wernher von Braun. Although Obert's work was crucial in stimulating the development of rocketry in Germany, he himself had only a limited role in that development. Alone among the rocket pioneers, Obert lived to see his ideas become reality. He was Braun's guest at the July 16, 1969, launch of Apollo 11. Other space pioneers, although Tsiolkovsky, Goddard, and Obert are recognized as the most influential of the first-generation space pioneers, others made contributions in the early decades of the 20th century. For example, the Frenchman Robert Esnault Pelterie began work on the theoretical aspects of spaceflight as early as 1907 and subsequently published several major books on the topic. He, like Tsiolkovsky in the Soviet Union, and Obert in Germany, was an effective publicist regarding the potential of space exploration. In Austria, Eugen Zenger worked on rocket engines and in the late 1920s proposed developing a rocket plane that could reach a speed exceeding 10,000 kilometers, more than 6,000 miles, per hour and an altitude of more than 65 kilometers, 40 miles. Interested in Zenger's work, Nazi Germany in 1936 invited him to continue his investigations in that country. Early rocket development. Germany. It was space exploration that motivated the members of the German VFR to build their rockets, but in the early 1930s their work came to the attention of the German military. In 1932 Wernher von Braun, at age 20, became chief engineer of a rocket development team for the German army. After Adolf Hitler came to power in 1933, Braun was named the civilian head of that team, under the military command of Walter Robert Dornberger. To give Braun's engineers the needed space and secrecy for their work, the German government erected a development and test center at Peenemünde on the coast of the Baltic Sea. There they developed, among other devices, the V-2, originally designated the A-4, ballistic missile. First launched successfully in 1942, the V-2 was used on targets in Europe, beginning in September 1944. Although built as a weapon of war, the V-2 later served as the predecessor of many of the rockets used in the early space programs of the United States and the Soviet Union. As World War II neared its end in early 1945, Braun and many of his associates chose to surrender to the United States, where they believed they would likely receive support for their rocket research and space exploration plans. Later in the year they were taken to the United States, as were their engineering plans and the parts needed to construct a number of V-2s. The German rocket team played a central role in the early development of space launchers for the United States. United States. In 1936, as Braun was developing rockets for the German military, several young American engineers led by graduate student Frank Molina began working on rocketry at the Guggenheim Aeronautical Laboratory of the California Institute of Technology, GALCIT. Molina's group was supported by the eminent aerodynamicist Theodor von Karman, GALCIT's director, and it included Chinese engineer Qian Shesen, who in the 1950s returned home to become one of the pioneers of rocketry in China. In 1943 Molina and his associates began calling their group the Jet Propulsion Laboratory, JPL, a name that was formally adopted the following year. JPL soon became a center for missile research and development for the U.S. Army. Following World War II, those weapons were adapted for use in early U.S. space experiments. After 1958, When it became part of the newly established National Aeronautics and Space Administration, NASA, JPA adapted itself to being the leading U.S. center for solar system exploration.